Hello everyone, my name is Mr. Shabani Mchomvu, and today we are going to learn a topic of algebra, specifically on the part goes by the name partial fractions. Partial fractions, from the concept of the complex algebraic fraction, we can say these complex algebraic fractions can be expressed as the sum of two or more simpler fractions, known as partial fractions. So the number and the form of the partial fraction of an algebraic fraction, for example, this one here, we have the numerator expression and the denominator expression of a certain partial fractions. Now, how can we form the numbers of partial fractions from these expressions? Now, as you can see here, f of x is 2x plus 5 as a numerator expression with the factor, linear factor, and the g of x equals to product of some factors expressed in different form. For example, this one is linear, but also linear but repeated, and this is a quadratic factor. Now, in the denominator expression, where we have numbers of factors, linear, repeated, or quadratic factors, now we can try to use that concept of the denominator expression to formulate or to express these complex algebraic fractions into different forms connected by the operators, either plus or minus. Now, in the g of x, as you can see here, there is a non-repeated linear factor of the form axc plus c b. This one here, xc plus 1. This is having the form of the linear expression. But also xc minus 2 bracket square, that is a repeated linear factor. When we say x minus 2, x minus 2, that is a linear factor, but when you x minus 2 now cubic, it is also a repeated linear factor. But the last one that we have here in the g of x, it is x squared plus 3. So this x squared plus 3, that is a quadratic factor, but it's a non-repeated quadratic factor, like this one. That is a non-repeated quadratic factor because we have a quadratic term, a term with the exponent 2 to the variable of x. Now, if that to be the case, so we are going to see 3 examples that how we formulate these partial fractions from the idea of the g of x nature. As you can see, linear factor, repeated linear factor, and the quadratic factor. So let's go to example on how we change the complex algebraic fraction into partial fractions. Example number 1. Maybe express 6 over x plus 3, then x minus 3 as a partial fraction. Yes, now the problem is just look like that. So solution. So the first thing that we are supposed to do, we have to check our denominator expression. We have linear factors, x plus 3 and x minus 2. So none of them is repeated, and they are just the linear factors. So what we do, now here it will be 6 over x plus 3, now x minus 3 equals to what? So I said earlier that the number of the partial fraction that we are going to form depends on the nature of the denominator expression or factors. So if we have the linear factor x plus 3, it means here now we introduce a constant that will be a over a linear factor, that is x plus 3. Now we have another linear factor x minus 3, so that will be the second constant b over x minus 3. Now, how do we express these a as constant here? It means when the highest degree here to this linear factor at the denominator x plus 3, which is 1 here, it means now we reduce this one by 1. So it becomes a x raised to 0. That to say a. The same applied to here. B over x minus 3, it means it was supposed to be, the highest degree is 1, so we reduce the degree by 1. So it becomes bx raised to 0, which is the same as b. That's why these constants, a and b, just look like that. Now from there, so we are going to deal with the right-hand side. Here we find the LCM, that is our denominator expression, x minus 3. Then now, this divide by this, we get a, we times x minus 3, we plus b times. Now the whole product expression divided by x minus 3, this goes. So it remains x plus 3 times b. So that is how now we get. After there, we are going now to write the expression that we have, x plus 3. Then here to the denominator, we have x plus 3, then x minus 3. And here to the right hand side, we have something like that. Now we equate. The only issue here is to just equating. So because denominator expression look the same, it means also numerator expression will be the same. So we equate the numerator expression. So it will be 6 equals to, we open the bracket, ax, a times negative 3, we minus 3a, then we plus bx here, b times this much, we plus 3b. So now this 6 is constant. It means it goes with the other constant that are lacking the variable x. So 6 goes with the negative 3a and the positive 3b. But these terms with the x, it means have to be equated by the terms at the left-hand side with x. So if no term with x here to the left-hand side, it means now we are going to introduce 0x. So it becomes like 0x with plus 6 equals to ax minus 3a plus bx plus 3b. So 0x is less small to what? All the terms with x. That is ax with plus bx. So here once simplifying, it means here x goes, so remaining with 0 equals to ax plus b. And this now we term it as equation 1. Again, coming to the constant numbers, that 6 goes with all these constants with the term that have no x. That say 6 is less small to negative 3a with plus 3b. So this now becomes the second equation. Now on solving algebraically, then we have, what do we have? So we take a plus b equals to 0 and negative 3a plus 3b equals to 6. So once simplifying here by 3, it means when you divide by 3, this becomes negative a plus b equals to 2. So we have modified the second equation, and it now becomes neg a plus b equals to 2. So this is number 1. So number 2, it becomes negative a with plus b equals to 2. Yes. So on solving algebraically, maybe we can apply the concept of elimination method. Starting eliminating maybe a, later we come eliminating b. So if we introduce plus here, it means we are going to eliminate a. So we solve for b. So It means here now eliminating A, solving for B. Solving for B. So this becomes A plus negative A is 0, but B plus B, we get here 2B equals to 0 plus 2, we get 2. So the value of B becomes 1 when we divide by 2 both sides. Also, eliminating B now, solving for A. What exactly do we have now? So it becomes A plus B, which is 0, neg A plus B, which is 2. So we introduce minus operator. So A minus negative A, we get 2A, but B minus B, we get 0, equals to 0 minus this much, we get negative 2. So once dividing, so we get the value of A is negative 1. After having such answers for the constant A and B, so we are going now to plug them. We are going to insert them where A and B. So now it becomes the complex algebraic expression 3, then x minus 3 is less small to what? A, it is negative 1 over x plus 3. We plus B now over B. The value of B is, here we've got 1. So where B now we put 1. And here is x minus 3. So having reached up to this point here, now we can say now this complex algebraic fraction is expressed as partial fraction. As you can see, two fractions which are here now. Okay, this is about example number 1. Now let's switch to example number 2. So now we are going to see example number 2, that is 3x plus 1 over x minus 1. Then the other factor that we have here is x squared plus 1. So we need to express this complex algebraic fraction as a partial fractions. So now, on investigating or observing the factor that we have here to the denominator of our expression here, we have the linear factor x minus 1, but also we have a quadratic factor. So what do we do here? Solution 3x plus 1 over x minus 1, then x squared plus 1. So this linear factor x minus 1, how to express it as a partial fractions? We introduce the constant a over x minus 1. But for the case of quadratic factor, how it can be expressed now into the partial fractions, now we are looking here, because it's a quadratic term, has got a quadratic term, this factor here, it means here to the numerator, it has to be linear factor. So it goes like bx, now we plug the constant c, over that x squared now plus 1. After reaching to this part here on the right hand side, so we are going now to operate them. So the first thing that we do, we find the LCM. That is x minus 1, then x squared plus 1. The reason here, we need to find the values of constant a, b, and c. After getting these values of the constant, then now we insert it into these separate fractions. From there, we can express it as a partial fraction, this complex expression. So now taking this now, divide by this, we get here a times that x squared with plus 1. Now we plus that bx plus c. Now we times what? So all these divide by that, it means we remain with x minus 1. So time that much, x minus 1. So from there, because now the denominator expression from the left hand side and right hand side will be the same, so we compare the numerator expression from both sides. So here it becomes 3x plus 1 equals to what? Now a x squared plus 1. Now we plug this bxc plus c, then xc minus 1. Now this we can apply the cover rule. So as we can solve now for the a, b, and c, these constants. So what we do, we expand here. We get ax squared, we plus a. Now we plus here, it becomes bxc square minus bx. This time that we get cxc, c times negative 1, we minus c. So we end up to a thing like that. So after reaching here, we collect the like terms. Collecting the like terms. So we are trying to check the quadratic terms, ax squared, bx squared. So this can be to 1 plus bx squared. Remember the coefficients of their terms and the sign, that is plus. So we connect them by plus. Then now the other one with x raised to 1. We have minus bxc and the plus cx. So this now become minus bx, we plus cx. Then the other part is for the part of constant. Those terms that are missing variable x. Here we have a, and we have this c here. So it becomes plus a minus c. Now, to the left-hand side, we are having a term with a variable x with exponent 1, and we have a constant. So we don't have a term with a quadratic with the x squared. So what we do, we need to introduce it. So here it becomes 0x squared, we plus 3x, we plus 1. So if you have written like this, has no any kind of difference with 3x plus 1, because this quadratic term, the coefficient is what? Is 0. So from here now, we can equate. So we equate the terms. So 0x squared, we equate with ax squared, we plus bx squared. Now, on cancelling x squared, it means when we divide by x squared throughout, we remain with 0 equals to here a, now we plus b. So this now becomes our first equation. Again, coming to x raised to 1, 3x equals to negative bx, we plus cx. Now on dividing with a common variable x, at every term it becomes 3 equals to negative b, we plus c. That becomes the second equation. And lastly, we come to the constant 1 equals to what? This 1 equals to a minus c. So this will be now our third equation. So on solving now, on solving algebraically, then we have so a plus b equals to 0, then negative b plus c, the second equation, equals to 3, and the last one, a minus c, equals to 1. So we find the possibility of solving now for the value of a, b, and c. How? It means we need to introduce one variable in terms of the other, so as we can remain with two variables as a technique of solving these equation algebraically. So from here, I can use equation 1 here to find the value of b in terms of a. So from here, a plus b equals to 0, I can say the value of b equals to negative a, because we take this a to the other side. So it becomes 0 minus a, which will be the value of b. Now from this relation, we substitute here to the second equation. And now we see what we have. So where b now, I just put negative a. So it becomes negative a with plus c equals to 3. That becomes a plus c equals to 3. So maybe this we can just call it the fourth. Question number 4. And now remember, in question number 3, we have a minus c equals to 1. So here, from equation 3 and 4, now we have the constant a and c, where now it is possible to solve for the value of a and c, then coming back here to solve for b. So by using now elimination method as part of algebraic solution, if we eliminate a or c, then we see what we have. For example, when we eliminate c now, we start by adding. So if we add, we'll get 2a here. It means c plus negative c goes. So here we'll have 3 plus 1, we get 4. So the value of a now becomes 2 when we divide by 2 both sides. Again, when coming to eliminate now a, it means now we solve for c. So now we apply minus operator. A minus a becomes 0. Now c minus negative c, it becomes 2c positive. Equals to 3 minus 1, we get 2. On dividing by 2 both sides here, the value of c becomes 1. Because 2 divided by 2, now we get 1. So from here now, our b now equals to negative a. So since a, it is 2, it means now the value of b becomes negative 2. So now this become the values for the constant a, b, and c. So what else now? It means now we are going to plug the values of a, b, and c. So as we can form now the partial fraction from this algebraic complex fraction. So from here, problem now becomes 3x plus 1 over x minus 1, then x squared plus 1 equals to what? What is a? A, remember we got is 2. So it is 2 over x minus 1. Now we plus, the value of b is negative 2. So here it is negative 2x. Now the value of c, it is 1. So we plus here 1, then over x squared plus c 1. So now here becomes the partial fraction. On further simplification, you can say it is 2x minus 1, then we plus 1 minus 2xc over x squared plus 1. Up to that point, you have expressed this complex algebraic fraction as partial fractions. And you can see we have 2 partial fractions. Now that is example number 2. Let's switch to example number 3 to see the repeated factor. So let's see example 3. That will include the repeated linear factor. For example, express 5x plus 1 over 2x plus 1 bracket square is a partial fraction. Yes. So here now, solution. We have noted that our denominator expression having linear factor repeated twice. So what we do now, this 1 over 2x plus 1 that has repeated twice, how do we express it in partial fractions? Now, if the expression here is linear and is repeated, what we do, we just introduce the constant a over that linear factor. Now we plus the constant b, but here remember is we just go times. Maybe here if the exponent is 2, it means we go when the exponent is 1 until we reach that higher exponent. And remember the factor here inside, it's linear. So here it means to the numerator, it has to be reduced. The degree of the independent variable has to be reduced by 1. So it is ax power 0. So if that to be the case, it means here is ax power 0, that the degree 1 has been reduced by 1. So this is the same as a. That's why you see this constant a here. But also coming to b, still the factor is linear. So it's the same as say bx power 0. That is the same as b. As you can see this b here. So now 2x plus 1. But now remember here the exponent was 1. So we reach here now 2, we stop. Because the highest power is 2. So from this idea here now, when we find the LCM, it means from this 5x now plus 1 over 2x plus 1 bracket square, now it will be a over 2x plus 1, we plus b over 2x plus 1 bracket square. So from there, we find the LCM. So the LCM will be 2x plus 1 bracket square, will be the same as here. So it will just look like 2x plus 1 square, because we have the same factor that are repeating. So when we take this divide by that, it means now it becomes a times, here remains 2x plus 1 plus b. When we take this one divide by that, it means it is 1. 1 times b, now we get b. Remember here we have 5x plus 1 over 2x plus 1 bracket square. Since the denominator look the same, now we compare the numerator expression from both sides. So it becomes 5x plus 1 is less more 2. Here you can open the bracket, 2ax, we plus a, now we plus b. From there we do the same thing, that we compare the terms with x and the constant to constant. So it becomes 5x equals to 2ax. So when simplifying, now we get 5 equals to 2a, whereby the value of a now, it is 5 over 2. Again, this one here equals to a plus b. So now we are having two expressions. A equals to 5 over 2, but also 1 equals to a plus b. Now on solving algebraically, so on solving by direct substitution, what exactly do we have? If a is 5 over 2, so from here a plus b, which is 1, and now we know a, it is 5 over 2. So here becomes 5 over 2 plus b equals to 1. So the value of b becomes 1 minus 5 over 2, which equals to, the LCM is 2. So we get 2 minus 5. So b becomes negative 3 over 2. So from our problem here, this complex algebraic expression now, that is 5x plus 1 over 2x plus 1 bracket square equals to what? A, now the value of a is 5 over 2. So it becomes 5 over 2, that will be 2 times the 2x plus 1, this one here. Now we plus the value of b, that is negative 3. So that's negative 3 and this additional operator. So when you times, it becomes here minus. So it becomes minus 3 over 2 bracket. Then we have our linear factor 2x plus 1 bracket square. So from there, it means now we have splitted this complex algebraic fraction into two partial fractions, as you can see here. Thank you.